I moved to University of Bath, and I'm currently leading the Applied Superconductivity Research Lab here.
So nice. I saw the number of projects that you have undertaken. It's great.
Yeah, I think it is an exciting and a growing area.
Yeah, sure. Yeah, I don't know how we have not been much. Yeah.
Vijana ma'am, shall we start?
Hello.
Vijana ma'am, hello, Vasanthi.
Yeah.
Suraj. Yeah. Suraj. Hello, Suraj.
Hello, am I audible?
You want
Yeah. So we'll start.
Suraj, you want her to do the presentation?
No problem. Let it be there. No problem. So Sharika, start.
Okay. Good evening, everyone, and welcome to the webinar on integration of superconducting fault current limiters and DC circuit breaker for DC network protection, organized by IEEE IAIE PELS Joint Chapter Kerala. Today, we have our speaker, Dr. Siaose Pei, Assistant Professor at University of Bath, United Kingdom, who is proficient in the domain of superconducting fault current limiters. Now, I would like to invite Dr. K. Pichana Kunju, Chair of IEEE IAIE PELS Joint Chapter Kerala, for the introductory address. Pichana ma'am, please.
Yeah, good evening, good morning, good afternoon for all the ambitious participants of this webinar. It is a great opportunity for us to host the webinar by Dr. Siaose Pei. It's a great opportunity because basically we come across people who are working in power systems, especially into the power system protection side. Usually it is occupied by the male dominant team. But now we have a very vibrant lady who's coming from England and basically from China, I suppose.
Yes.
Pei, Dr. Pei, you're basically from China.
Yeah.
So it's a great opportunity for us to have you here. And we look forward to hear from you quite a lot because we had taken the DC circuit and low voltage DC distribution systems as one of our key areas to work from by the IEEE itself. And she is actually a person who has published a lot of papers in this area of fault current limiting and protection, especially in DC. As to begin with, I know she'll be starting with the problem of why there is a problem in DC circuit breaker. We always try to teach our students in power systems to start off that sine wave is our luckiest thing because you have zeros in between. But you don't have a zero in a DC circuit. So how to break the circuit when you have a fault in a DC circuit. So this is a great opportunity for us to hear from you, ma'am. And we look forward to hear from you mostly your experiences also, because I've seen that you have done a lot of projects with various industries while you were working for the past 13 years at UK. So we look forward to your words, ma'am. A hearty welcome from our side, ma'am. Welcome.
Yeah, thank you very much for your introduction, and thank you very much for your invitation. So good morning, good afternoon, and good evening, everyone. Thank you very much for attending this seminar today. I'm Xiaoze Pei from University of Bath, and I have been in University of Bath since 2017. And I'm currently leading the Applied Superconductivity Research Lab and the research group here. So we have a postgraduate researcher in our group, mainly focused on superconducting fault current limiter. And we also have a few students looking into the DC network protections and some of the converter design. So the talk I'm going to talk about today is the integration of the superconducting fault current limiter and the DC circuit breaker, mainly used for the DC network protection. And my talk will cover the following area today. So initially, I will start with the introduction, why do we need the superconducting fault current limiter for the power application? And then we will look at into the superconducting fault current limiter requirement and what is the general technology around at the moment. So initially, we will also look into the AC grid and protection. And I will take you through a few of the superconducting fault current limiter recent demonstration project around the world to give you an idea what is the current state of art of technology. And then I will move on to the new exciting emerging area of the medium voltage direct current system, because this is more related with there are more DC generation, for example, PV panels, and also DC load like the electric vehicle battery charging system. So there is a growing area for the medium voltage direct current system. I will talk about some of the applications. And it's already mentioned for the DC, because there is no zero crossing. So what to do with the DC network protection is always a big challenge. So I will do a review of the current DC circuit breaker technology, and then present some of the research activity at University Bath, what we have done around this area. So I will make a start about the why do we need a superconducting fault current limiter? That is the first question. Because we know that the power system, the fault happens. It can be due to the natural disaster like a hurricane, lightning, or it can be due to some of the human errors like the aircraft hit the transmission line or the distribution line. And this is posing quite a lot of a challenge to the development of the distribution network and the transmission network. That is because over the last decade, the general need of the electricity due to the human lifestyle, the demand is increasing. And also there are integrated of the distribution of renewable generation, like the PV solar panels and the wind generations integrated into the existing grid. So which means there is a increasing of the fault current levels. And this has been a serious problem for the land-based power system, because when the power system was initially designed, all the circuit breakers and the protection unit was designed based on the maximum capability in the time of designing. And because this is a developing area, like with the increase of load and the increase of the generation, so which means the fault current levels is keep increasing. So, and a lot of the fault current levels is already approaching to the maximum that the circuit breaker is able to handle. So what is the options? The option is, firstly, you can consider to upgrade all the circuit breakers in your substation, but this is very expensive and also a lot of the civil engineering work involved. Or superconducting fault current limiter is a new technology that is able to limit the fault current level. So you only need to put this unit into your grid, and then the rest of the system can maintain the same. So what is the requirement for superconducting fault current limiter would be, it have to provide very reliable and very rapid current limitation during the fault. And when fault cleared, it needed to have the functionality to recover automatically from the fault condition as well. So this is a typical requirement for superconducting fault current limiter. So initially, this is the normal operating stage that you can say this is a normal load current. And when a short circuit fault happens, the red curve is a prospective fault current. So you can say the fault current can be very high, can be tens of times or even hundreds of times of the load current. And this is a sudden increase of the fault current, which may bring in the damage to the existing equipment, and also the circuit breaker may run out of capability to interrupt this fault current. So that is why when we design a superconducting fault current limiter, our objective is to limit the current into the blue line to a significantly lower level. And we also hope this unit have low losses during the normal operation, so it doesn't change the operation of the existing grid. And then suddenly increase to a high impedance, so it can be a high resistance or high inductance to limit this fault current levels, so that all the protection unit can still function as expected. So why are we talking about superconducting fault current limiter? Because the superconducting material have very high current density, and also it doesn't have losses under the DC operating condition. So what is the commonly used superconducting material that is used for the fault current limiter application? It is mainly, we call it high temperature superconductors. So the first two high temperature superconductors, which means they can operate into the liquid nitrogen, because nitrogen got 78% in the air. So it is a very easy and cheap to get liquid nitrogen. And the first generation high temperature superconducting material, it is a multi-filament B2223 tape. And Sumitomo in Japan, it is one of the leading supplier for this tape. So when we look at the structure-wise, it is firstly to manufacture into a single filament structure, and then the multi-filament is putting into a tube and pressed into a tape shape. So normally this is manufactured with a powder in the tube technology, and this is a very matured manufacturing technology. However, you can say it uses quite a significant amount of the silver in the raw material. So which means the cost of the this type of high temperature superconductor is quite expensive. And then it is the second generation yttrium barrier copper oxide coated conductor. And this is a layered structure that has like a metallic subscript, and then the buffer layers, and a very thin layer, normally only 1 micrometer or 2 micrometer of the superconducting layer. And so because this is a very complex manufacturing process, but it is a very matured technology now, and there are more than 10 commercial suppliers, for example, American Superconductors, and also Shanghai Superconductors, and Sunan, who are able to provide this YBCO superconducting tape. And this is the main drive force for the superconducting cable and the fault current limiter design area. And also I would like to mention another superconducting material, which is called magnesium diboride. So magnesium diboride is got a very cheap raw material, and the manufacturing process can use a powder in the tube process, so which is the same as the first generation superconducting tape. So which means it's got low cheap raw material and also affordable manufacturing process. The only limitation for the application of the magnesium diboride, it is because the operating temperature is between 20 to 25 Kelvin. So which means it's not able to operate in liquid nitrogen. So when liquid nitrogen burns in this temperature, this is already like a solid nitrogen for this operating temperature. So it's normally need a closed loop cooling system, which adds the cooling system into the cost. Because when we look at application, we need to look at the system level cost, the material cost, and the cooling cost. So this is the 3 superconducting material tape that has been used in the last decade. And what is the main types of superconducting fault current limiter? So the first type is which I'm going to focus today would be the resistive type superconducting fault current limiter. So this is directly using the superconducting characteristic. So what it means is when the current in the superconducting tape is low, so the tape maintains in the superconducting state, so which means is no losses for DC condition, and very low AC losses. So this means when you put it into the grid during normal operation, basically is invisible. And then when a very high fault current happens, this high fault current value would drive the superconducting tape from the superconducting state to its transition period and then to the normal conductor state. So which means it changes into a resistance and into the power grid to limit the fault current. So this is directly using the superconducting characteristic. And this is a very simple concept and a very compact structure. I'm going to show you some of the demonstration projects in using this type. But one of the biggest challenge is that superconducting tape and module sit in the liquid nitrogen, and it have to have a current leads which connected the room temperature to the low temperature environment. And considering of high voltage application, so the design of this current leads is one of the biggest challenge for the resistive superconducting fault current limiter. And in the meanwhile, it also have more like a inductive type of superconducting fault current limiter. The first one, the DC biased iron core or centrated iron core fault current limiter. This have been able to demonstrate at 220 kilowatts as well. So how does it operate? It basically, the green one is a superconducting tape. So it's energized a DC current, which put the magnetic core into the saturation condition. So when the magnetic core is connected to the power grid, and you can consider the magnetic core and the air core now because it's in the saturation stage. So very low inductance connected to the grid. And when the fault happens, this fault current would drive the magnetic core out of saturation, which now becomes a high inductance adding into the circuit to limit the fault current. So you can see in this process, the superconducting tape is not quenched. So which means it can have a faster recovery stage. So the quench is a stage that the superconducting tape transient from the superconducting state to the normal state. And also it have different, another inductive fault current limiter, which is a shielded iron core. So the key advantages is doesn't require a current leads to the low temperature. But however, it does have the iron core structure, so which means the whole unit could be quite heavy. So in the talk today, we are going to mainly focus on the resistive type of fault current limiter. We look into this because we are looking into the transportation electrification. So we really want to keep the unit very compact and lightweight and high power density in this area. So I will take you through a few existing demonstration projects around the world, because the superconducting technology and the development of tape is reasonably, so it's like a very close to commercialize in this area. So this is a M-City superconducting tape and fault current limiter demonstration project. Basically, it's connected to 2 substations in Germany, and the distance between them, it is 1 kilometer. So originally, because one of alternative technology option is like using the high voltage system, like 110 kilowatts to connect those 2. But because one of substation is very close to the urban area and you want to reduce the current level and still able to fit the curve. So that is why the superconducting cable, which have a very high power density and is able to do the connection at a lower current value, which is 10 kilowatts. So it's connected the 2 substation and 1 kilometer superconducting tape. And also it investigates about the cable joint. So how to join the 2 superconducting table together, and the fault current limiter to limit the fault current level, for the protection purpose. So this has been running for a few years now, very successful. And in Korea, it also have the superconducting for current limiter demonstration project, both under the distribution voltage level, which is 20.9 kilowatts for Korea. And this is an indoor installation, which is also a resistive type superconducting for current limiter, but it does have the circuit breaker to provide extra time for the recovery. And a single phase development for the distribution voltage level, which is 154 kilowatts. So what you can say, so this is the cryogenic system, so which is a cryostat, which have fill in the liquid nitrogen. And the top bushing here, so this is the current leads from the room temperature down to the cryogenic temperature of the superconducting tape. And this is one of the key challenges in the design, because firstly, it needed to take the temperature gradient from 290, like 300 Kelvin in room temperature down to 70 or 60 Kelvin. That is a temperature gradient. And secondly, it needed to transport the very high current value. And thirdly, is also a triple connection between the vacuum and the environment. So that is a lot of the development around the bushing design in this area. So the Russian have the 220 kilowatts demonstration project, and this is a 3-phase project which has been commissioned in 2019. And there are another 6 more project in planned in Moscow. So it's moving very quickly into trying to commercialize the fault current limiter. And China is also very active in this area. So China developed this 220 kilowatts system, which is tested in 2008, and which is an AC system. And China has also built the first distribution level, distribution voltage level for the DC application using the pancake structure of the superconducting fault current limiter. So this is an overview about what is around the world at the moment. At the University of Bath, we had a funded project from the UK government trying to look into how to design the superconducting fault current limiter for an electric propulsion aircraft application. I will talk about a little bit more background later as well. So for the electric aircraft, it will require very high power density and very high efficiency. So we're looking into the helical type of the superconducting fault current limiter. And this winding have two layers. So one inner layer and another outer layer. Because it's a resistive superconducting fault current limiter, you normally try to reduce the inductance here. So that is the current going the opposite direction to cancel the main magnetic field. So which means this is a low inductance, which doesn't impact the system operation. So we're looking into 2 structures that connected those 2 coils in parallel, which increase the current value. And we're also looking into connected those 2 winding in series and trying to understand what would be the operation difference. Because I mentioned the superconducting doesn't have any losses on the DC condition, so which is perfect for DC application. It does have some AC losses. So the measurement of the AC losses of the superconducting coil is always a very difficult topic, because the losses is so low. You need to have a very accurate, dedicated system to do the measurement. So at the university lab, we have the power amplifier, we have the locking amplifier to generate the signal at a different frequency. Then we use a power amplifier and the transformer to increase the current level. And in testing, we put the fault current limiter coil into the liquid nitrogen, and we developed the Rogowski coil for the accurate current measurement. So when we measure the superconducting fault current limiter, the first thing we need to measure what is the critical current of the superconducting tape, because this is a very important aspect. We need to make sure the critical current is higher than the normal operating current, so it's maintaining the superconducting state during the normal operation. And 1 microvolts per centimeter is normally used criteria, and based on our design, the critical current is very similar to the critical current of the tape. So which means during the winding process, there is no degradation. And then we measured the AC losses for 2 winding types. One is connected in parallel, one it is connected in series. So what we found that the losses at a different frequency and is this when we look at the loss per cycle, it is the same when the coil is series connected, because basically the series connection makes sure the current in those 2 coils is exactly the same, and then it's leading to a lower losses. When we investigate the parallel connection, we found the parallel connection response different at a different frequency. And also it have higher losses compared with the series connection. That is mainly due to the current in those 2 strands have a minor difference in current sharing. So in the parallel connection, we really need to be very careful to maintain the constant, like a contact resistance and also the coil inductance exactly the same to ensure it is a very evenly current sharing. Otherwise, this would lead to the increase of the AC losses in this area. So AC losses is important for the AC superconducting fault current limiter. And then a second important area would be, how does it respond to a fault current? What is the response time, and how long does it take when the fault is cleared in the system? So in the lab, we developed a 3 kiloamps AC fault current limiting test circuit. So we developed a program that we are able to control some of the switch box to simulate the normal operation, and then the fault condition, and then the recovery condition. We can parameter all those lengths of the fault duration and observe the recovery as well. So this is some of the experimental result on the helical bifilar coil. When the perspective fault current is 1,200, so you can say the blue curve, it is the perspective fault current. So without fault current limiter, it will go up to 1,200. And then with the fault current limiter we designed, the current is limited to the red line, so which is just below 400 amps. So you can say this is a significant reduction of the fault current in the system. And we observed what is the resistance across the coil. So when the fault current is is just a few times of the critical current, you can say this is a fault for 100 milliseconds. When the fault is removed and back to the recovery current, similar to the normal current, you can see under this condition, superconducting fault current limiter is able to recover very quickly to its original state. So it so that if a fault happens, it can go back to limitation and no resistance back to this level. And when we doubles the perspective fault current, so increase to a higher level, and what we can see, the fault current is limited from 2,200 amps down to a few hundred amps. So this is again very effective fault current limitation. But what happens is when we're looking at the resistance of the superconducting coil, so over the 10 second and so over the 100 millisecond, that the superconducting coil limits the fault current. And then because the temperature is still pretty high when the fault cleared. So in this case, that the superconducting fault current limiter is not able to recover. So it still have a high resistance even fault is cleared. and then it probably would struggle to recover under the loaded condition or takes longer to recover. So we do need to pay attention to how long is the recovery time. And in the grid application, normally it requires, like, for example, between 1 second or to 3 seconds for the recovery. And we take a look at what would be the quench behavior when the coil is connected in the parallel connection. And we can say it is very effective fault current induction reduction. And this is a very interesting result is when the fault is cleared, we clearly can say is half the capability that is able to recover under the loaded condition, but it just takes probably a few hundred milliseconds to recover. So we take to summarize this section, we design the superconducting fault current limiter, and the exam is detailed mechanism, how to reduce the AC losses, and what is the quench behavior, and also how it responds to different recovery conditions. So those provide very important guidance for the design of the superconducting fault current limiter. So I will draw a close for the AC part, which is more conventional AC grid. Now I'm going to move into the medium voltage DC grid and go through about the DC fault current limitation and interruption in this area. Why do we pay attention to this? Because there is a very growing need for the medium voltage direct current. So this is a feasibility study leading by SIGRE, and it's looking into the internal driving force. For example, for the DC network, it can provide improved power quality, and also it improves the stability of the DC power supply as well. And it does make sense if we have increased the DC generation, like a PV solar panel, and also large DC load, for example, the data center and the electric vehicle charging station. So if all those functions combines together, which means the system efficiency using a medium voltage DC would be much more efficient compared with a conventional AC system. So that is why there are more and more research and also demonstration projects started to looking into the medium voltage DC grid. I will give you a few examples. So the first example is the offshore wind connector. This is to looking into a case study in the Scotland and North Sea area, looking into how to connect the how to do the wind connectors in the wind farm, and it is proposed to use a medium voltage DC, and the cost benefit is quite significant for this application. And this is carried out by TNE, one of the consultant engineering consultant, engineering and energy consultant company in the UK. And a second area is a medium voltage DC has been talked about a lot for the transportation electrification area. So for example, the roadmap for the future marine application is started to look into the medium voltage DC up to 6 kilowatts, because this, firstly, it reduces power conversion, and secondly, it doesn't need a synchronization of different AC system. And also it can provide a very high power quality if there is a pulse load in the marine application. And a third area would be the DC system for the onboard aircraft system. So for example, the leading players, NASA is looking into this N3X concept aircraft, which using the superconducting DC microgrid, because when we're looking into like a zero, the emission target and zero emission target, so then the electric aircraft is the only possibility to provide this. And when we consider the large-scale electric aircraft, we have to consider superconducting technology, because the conventional using like a copper cables, it's just simply too heavy for this application. So Airbus is also have the same idea. They have three like a 0E concept aircraft, which is powered by hydrogen. So liquid hydrogen is a perfect combination with superconductor technology, because hydrogen not only provides the energy source and also provide the cryogenic environment for the superconductor technology. So recently, just a few months ago in 2021, Airbus have launched a demonstrator project, which is advanced superconducting and cryogenic experimental power train demonstrator, which looking into a DC distribution network to investigate the possibility to apply the superconducting technology directly onto the electric aircraft. And the fault current limiter and the circuit breaker is one of the key elements in this demonstration project. So now let's start to talk about what is a challenge. Why do we look into the DC circuit breaker? We know this is an emerging area, going to have more and more DC. So what is a challenge? And I put a very for an AC network that we have the current and the voltage is cross the zero twice in a cycle. So which means if we have a mechanical switch, we can interrupt the mechanical switch, and this current zero crossing would just help to extinguish the arc in the mechanical switch. But what happens with the DC? Because with the DC, there is no natural current zero. So which means the mechanical switch is not able to extinguish the arc. And secondly, in particular for the onboard system, because everything is quite closely coupled together, so which means it would have an even higher fault current levels and also have a very high rate of rise of fault current. So how do we dealing with this? We carried out a review in this area to look at what is the current technology. And for example, mechanical DC circuit breaker. So for the mechanical DC circuit breaker, it will have to have an auxiliary circuit, for example, inductor and capacitor resonant circuit, to create an artificial zero crossing for the mechanical switch that is able to extinguish the arc. And the benefit of a mechanical switch is it's a very mature technology, and it is a very low losses operation as well. However, one of the main problem is the operation speed of the mechanical DC circuit breaker is quite limited. The commercial solution at the moment is about 30 to 50 milliseconds. So this sounds slow, but for the DC, the DC fault current may already increase to a higher level that the circuit breaker is not able to handle. So the second option is a power device, solid state DC circuit breaker using the semiconductor device. And we know that, for example, for the IGBT and the IGCT control device, it's able to interrupt the fault quite quickly. However, it have a high on-state losses, so which means the impact the system efficiency. So that is why ABB come up with a hybrid structure. So what does it mean is that during the normal operation, the current goes through this mechanical switch. So this is a low losses path. And when the fault happens, this load commutation switch opens first, and which means the current in the mechanical switch would reduce zero and diverted to the main DC circuit breaker using the solid state devices. So the mechanical switch can open without a current and without arc. And then once it's able to withstand the system voltage, then we can open the solid state DC circuit breaker. Because the solid state DC circuit breaker only takes the current for a very short period of time, just a few milliseconds, 1 to 3 milliseconds. So, and the losses doesn't matter that much for a short period of time. So that is why this is a combination of the low losses during normal operation and then very fast interruption during the fault condition. So the research in our group is around the hybrid DC circuit breaker. So what we want to achieve is like we want to use the superconducting fault current limiter to limit the fault current level so that the hybrid circuit breaker is able to open reliably. Around this area, we're looking into 3 different topics. So we're looking into a new topology. So do we have other new topology around the hybrid circuit breaker? And then secondly, we're looking into the fast operating mechanical switch. How do we design this actuator to operate the mechanical switch? And then thirdly, we also integrate, also look at the how do we do the design of the solid state DC circuit breaker, because with a higher voltage and current level, we will need to the series and connecting of the semiconductor devices, what is the current balance and the voltage balance in the system. So with a new concept, we proposed a new concept with automatic current commutation circuit, which basically used a coupled inductor in the system. And when there is a fault current happens in the main circuit, then because those 2 inductors are coupled together, it produces a voltage that automatically driving the current out of the mechanical switch and commutated to the semiconductor switch. So we have already built one of the demonstrator in the lab. And this is some of the interesting results. So you can say this is a normal operating current, and the current goes through the mechanical switch. Once we create a fault, you can say the current started to increase. And this increase of the current would couple those 2 inductors together and then drive the current out of the mechanical switch. And then the mechanical switch can be turned off at the 0 current here, and current will be interrupted by the semiconductor switch after this. So this is a structure we proposed, and the key advantage is it have an automatic current commutation in the fault condition. So which means we are less relying on the detection of the fault in the circuit. And the second area, we're looking into the solid state circuit breaker. So we designed a prototype that have 2 IGBT connected in series and 2 IGBT module connected in parallel. So this is the system we are able to investigate what is the current sharing during normal operation and what is the voltage sharing during the interruption. Are we able to have a balanced system design? So we have built a prototype in the lab, and this is a 3D design and a control circuit. And in order to understand the behavior, we have some plugged model for the steady state operation and the dynamic operation. So in the lab, we set up a on-state, like a steady state test, trying to investigate the circuit breaker and the solid state circuit breaker on its own, putting the thermocouples to measure the temperature rise at different current level. So at the steady state, we can say the current sharing in those 2 IGBT is very balanced. So which means those 2 IGBT have a very balanced thermal behavior as well. And but what we can say here is with only a solid state circuit breaker carrying 150 amps, so the temperature rise from 20 degrees centigrade up to 50, and then it's pretty much stabilized. So we can say like the losses of the solid state circuit breaker is still quite high. That is the main reason the hybrid circuit breaker is mainly used. And then we investigate is the dynamic test to say when there is a change of the current, does it still balance? So we did the simulation, and then we did the experimental result. So we use a circuit to create a resonancy current to simulate the fault current. So you can say this is a total fault current from 0 rising to 1,000 amps. And this is the total current in two parallel branch, and this is the current in one branch. So we investigate the current, we can say in a dynamic change with our design, we are able to achieve very balanced current in those two parallel branches. And then when the current rises to 1,000 amps, we started to interrupt the current. And when the current is interrupted, we observe what is the voltage drop across the series connected IGBT. So we can say the voltage drop is very balanced around those two elements, and this is a total voltage drop. And so with our design, we are able to achieve a very balanced current during the dynamic steady state and the dynamic state. And at the interruption stage, we are able to have a very balanced voltage level across the series connection. So this is very important because this means we are able to use a series connection and the parallel connection to increase the current level and the voltage level of the DC circuit breaker. So the next step, we integrate the superconducting fault current limiter with the DC circuit breaker. So we use the fault current limiter to limit the fault current levels. So the prospective fault current levels is 3,000 amps, and you can say it's limited down to 1,200 amps. And then the solid state DC circuit breaker is able to interrupt the fault. So we are able to demonstrate effective fault current limitation and then very quick current interruption. So besides this, we're also looking into what is the operating system for the circuit, for the mechanical switch, because the current research project mainly using the Thomson coil is very fast operation, but it's got very limited efficiency. So what we have been looking into is like we propose to using the moving coil actuator, which is very similar to like a loudspeaker. So the permanent magnet create a magnetic field, and the coil is suspension in the air gap. When we drive a current in the coil, it will have a Lorentz force going up or down and the movement. So because the coil, we can design it very light, so light movement and very high efficiency. So we built a prototype in the lab, which is using the moving coil actuator and is able to provide a displacement of 5 millimeter within 4 milliseconds, so very fast. And we want to improve the operating speed even further. So we proposed a new development which have a compensation coil, which able to reduce the equivalent inductance of the coil. So very fast current rise in the coil and improve the efficiency. So in our recent published paper, we are able to achieve 3 milliseconds to achieve 5 millimeter displacement. And this is a new topology is under construction at the moment. So this brings to the summary of my talk today. We can see that the superconducting fault current limiter has been successfully demonstrated for the distribution network, transmission network, and the DC transmission network. And secondly, I want to say that like there is a very fast emerging market for the MVDC grid for the integration of the renewable generations and the DC load, and also for the transportation electrification. So that is why our research group is mainly focused on the DC network protection. So we believe the superconducting fault current limiter can offer very effective fault current limitation so that it allows the design of the DC circuit breaker to operate quickly and reliably. And we think this is a very promising solution for the DC network protection. So thank you very much.
Thank you, ma'am, for the wonderful session. So we'll be having
Thank you, ma'am, for your wonderful section. Participant can ask any doubts in the chat box. We will read it out.
Yeah, thank you very much for your invitation, and it is my pleasure. So if you have any questions, if you leave in the chat box, and I'm happy to take any questions. It can be related with a research project, or it can be related with personal experience.
I think there's no question, ma'am.
Okay.
Hello. Hello.
Yes.
Yeah, yes, ma'am. So my question from my side. So in the for a project, how far the circuit breakers, like how can we modify the present circuit breakers into an efficient for increasing the efficiency?
Okay. So if I go to the hybrid, if I go to this slide here, and for the are you talking about the efficiency of this mechanical operation of the mechanical switch, or are you talking about efficiency and the overall system?
Or the overall system, ma'am.
Okay, so I think it's like to improve the efficiency, which means the reduction of the losses. That is why one of the area, because originally you can say is using the current limiting reactor, and this current limiting reactor would have a losses during the normal operation as well. So that is why we want to propose to use a superconducting fault current limiter. In this case, it almost have no losses during the normal operation. And then the second component is looking into the losses for the primary path that current normally goes through. So because one, it is trying to reduce the contact resistance of the mechanical switch. This is already quite matured technology. And then another important area is about the design of this load commutation switch, because load commutation switch is made of a low voltage MOSFET, and it normally uses quite a lot of them connected in parallel in order to reduce the losses. So this is why we come up with this new concept of using a coupled inductor to for the current commutation, because in this way we are able to remove the need of this load commutation switch and reduce the losses during the normal operation, which provide a high efficiency operation. So in general, in order to reduce the losses, and if already consider the cryogenic system, superconducting superconducting technology is a very good area to consider. And then to reduce the losses for the semiconductor part, it is quite commonly you use a parallel connection of the devices to reduce the losses. I hope this answers your question.
Yes, ma'am. Thank you, ma'am. So there is one question in the chat box. How is the quenching behavior for series and parallel wound SFCL in DC circuit breaking scenario?
Okay, yeah. So the question: how is the quenching behavior for series and parallel wounded superconducting fault current limiter in the DC circuit breaker scenario? Yeah, this is a very good question. So for this superconducting fault current limiter, we initially tested under AC condition, and we did take this coil into the we did take this coil into the DC condition as well, because I think the main so with a parallel connection, because we increased the current to twice or double of the series connection. So which means it increased the current level of the superconducting for current limiter, and also how to say, for the series and the parallel connection, what we make sure is like the current goes through those two winding. It is in the reverse direction, so it cancels the main magnetic field, and both of the system have a very low overall inductance in the system. And in fact, the series and the parallel behavior, it is quite similar. It's only that the rated current and rated voltage changes different for those two connections.
Okay, so thank you, ma'am, for the answer. So that's all from the Q&A side. So Shari, over to you.
Once again, thank you, ma'am, for your session. Now, I invite Dr. Vasandi V, Vice Chair of IEEE IEPEL's Joint Chapter Kerala, to deliver the vote of thanks. Vasandi, ma'am.
Yeah, thank you, Shariga. Good evening, good morning, and good afternoon. It was a fantastic session on superconducting fault current limiter, and Dr. Pai has explored a lot. And I'm sure all the researchers in this participant group must have gained a lot, and they could continue their research in this emerging area. So on behalf of Joint Chapter, let me express my sincere thanks to Dr. Pai. Thank you, ma'am. Thanks a lot.
Yeah, thank you so much for your invitation. It is my great pleasure to do this webinar today, and also it is a very challenging time to the world due to the pandemic situation at the moment. I do wish everyone take care of yourself and stay safe, and the situation will get better.
Yeah. Thank you, ma'am.
Thank you very much, Dr.
Yeah.
Pai. Dr. Pai. Please take care for yourself also.
Yeah.
Thank you.
Thank you and take care.
And thank you all the participants also.
Thank you. Thank you, our technical team. Thank you, Alan. Thank you.
So shall we stop the meet?